So may I welcome you all to Gresham College, especially those who are visiting for the first time, and to this lecture and book launch on the mathematical world of Charles L. Dodgson, better known by his pen name of Lewis Carroll. He used it when writing the Alice books, Alice's Adventures in Wonderland, and Through the Looking Glass, and even for some of his more mathematical writings, as we'll see. For Dodgson's day job was as a teacher of mathematics, as a mathematics lecturer at the Oxford College of Christchurch. Much has been written about the Alice books and Carroll's other writings for children, but there's been far less about his daily life as a mathematician. So 12 years ago, I wrote this book, published by Penguin, in which I tried to present Dodgson's mathematical interests in a light-hearted way for a general audience. But in fact, there are a few books and articles about his mathematics, but many of these are rather difficult to locate, and for some time there's been a need for a book that collects his mathematical activities in an interesting and accessible form into a single volume. And the book I'm talking about today hopefully fills this need. Published earlier this year by Oxford University Press, it covers a wide range of topics written by experts on Dodgson's mathematical writings from here and abroad. My co-editor was Amirouche Moktefi, who is a world expert on Dodgson's writings on logic and who wrote the logic chapter here and shared the opening chapter with me, introducing the whole subject. But before I introduce you to some of these topics, let me set the scene by telling you all about Dodgson's early life. He was born in 1832 into a good English church family in Daresbury in Cheshire, where his father, the Reverend Charles Dodgson, was the incumbent until 1843, when they all moved to Croft Rectory in Yorkshire. And there he and his 3 brothers and 7 sisters enjoyed a very happy childhood. They had lots of games to play, walks to take in the countryside, and puzzles to solve. And Charles used to entertain them all with magic tricks and also building a model railway in the garden. Remember, railways were just coming in around that time. And here's a complicated maze that he once constructed for his brothers and sisters. And according to puzzle experts, it was the first ever 3-dimensional maze designed with passages going over and under other ones, the first one ever designed. But that was much later. From the beginning, he was interested in mathematics, which his father taught him, along with Latin, Christian theology, and English literature. And as you can see here, it's reported that when he was a small boy, he went to his father and showed him a book of logarithms and asked, "Please explain." His father replied, "You're much too young to understand anything about such a difficult subject." But the young Charles thought this irrelevant, for he still insisted, "But please explain." He was also fascinated by geometry from an early age. And here's part of a 2-page note that he wrote on how to divide a right angle into 3 equal parts. You probably remember at school where you had to sort of bisect an angle, divide it into 2 equal parts. In general, you can't divide an angle into 3 equal parts, but you can for a right angle. And the young Charles wrote this when he was aged just 12 years old. That was the same age as he started to compose Latin verse. By this time, his father could afford to send him to school. First to Richmond School in Yorkshire, and then to Rugby School, where he delighted in mathematics and the classics, but disliked much of the rough and tumble of everyday school life. But while at Rugby, he was very successful. He won many prizes in a wide range of subjects. And his school arithmetic textbook was the latest edition of Francis Walkingame's classic text, which had been around many, many years earlier. And here are a few questions I thought you might like to see, which I copied. I copied from Dodgson's own copy, which is now in New York. And they're certainly not what you'd find in arithmetic school books today. For example, how many school books today would ask, what is the cube root of 673,373,097,125? Or, if the distance from London to York is 50 leagues, how many miles, yards, feet, inches, and barleycorns is this? where a league is 3 miles and there are 3 barleycorns to the inch. Also, if 504 Flemish ells, 2 quarters, cost £283, 17 shillings and sixpence, what must I give for 14 yards? And even this rather politically incorrect one, the Spectators Club of Fat People, though it consisted of 15 members, is said to have weighed no less than 3 tons. How much was that per man? I don't think you'd find that in many modern school textbooks. In May 1850, Dodgson applied to Oxford University, where he was examined in Latin, Greek and mathematics, and he was accepted at Christ Church, the largest college, where his father had studied some years earlier with great success, and where the young Charles was to spend the rest of his life. And he took up residence in January 1851 for a 4-year honours degree course in classics and mathematics. It's often said Oxford for the arts and Cambridge for the sciences. I don't think this was ever really the case, except for this particular case. You couldn't read for a higher degree in mathematics or something specialised like natural science unless you'd first done a degree in classics. Whereas in Cambridge it was the other way around. You couldn't do a degree in any other subject unless you'd all done a degree in mathematics first. And that happened just for a few years, and that may be why people said that, Cambridge for the sciences. But the history of Oxford mathematics is very, very strong, and it was only around this time that it was that way around. So his university studies consisted mainly of mathematics and classical and biblical texts, and involved 3 main examinations, starting in summer 1851 with his responsions exams, commonly known as Little Go, and continuing with moderations, finals in classics, and then his finals in mathematics. And his instruction was mainly in college with the college lecturer Robert Fawcett, shown on the right, and he also attended lectures by the professor of geometry, the Reverend Baden Powell, whose son was later to found the Boy Scout movement. His examinations are both written and oral, and as you can see, an Oxford oral exam was probably a rather terrifying experience. In the summer of 1854, shortly before his mathematics finals, he went on a reading party to Yorkshire with the new professor of natural philosophy, Bartholomew Price. Everyone called him Bat Price, possibly because his lectures were way above the audience. And Dodgson remembered him later in the Hatter's parody of Twinkle, Twinkle, Little Star, which went, Twinkle, twinkle, little bat, how I wonder what you're at, up above the world you fly like a tea tray in the sky. And so that bat is commonly thought of to refer to Bartholomew Price. And incidentally, you're all familiar with the Mad Hatter? Well, there's actually no character in the Alice books called the Mad Hatter. There's a hatter and a mad tea party, but you'll find no Mad Hatter. His mathematics finals exams took place at the end of 1854 and ranged over all areas of the subject, including such topics as calculus, gravitation, and optics. And here are some questions from an 1854 paper on geometry and algebra, and including a range of questions on arithmetic, geometry, algebra, number theory, and binomial coefficients. When the finals results came out, Charles Dodgson had been highly successful, gaining the top mathematics degree in the university. And as he wrote to his sister Mary, I have just been to Mr. Price to see how I did in the papers, and the result will, I hope, be gratifying to you. He then listed all those in the first class, with his name first, continuing, all this is very satisfactory. After finals, he stayed on at Christ Church, earning his keep by private teaching. And here's an extract from his diary for 1855. Got a note from Leighton, a gentleman commoner, who wishes to be taught some arithmetic for his little go, that's responsions, as well as the second book of Euclid. And on the left, here is the famous entrance, Tom Tower, designed by Christopher Wren. and on the right is the dining hall where he dined over 10,000 times, and which now seems to be known mainly as the dining hall of Hogwarts. In the same year, the old dean, that's the head of college, died and was replaced by a new one, the Reverend Henry Liddell, half of the team of Liddell and Scott, who compiled the Greek dictionary that amazingly is still in use by students even today. His family included their young son Harry, and also their 3 daughters, shown here with Alice on the right. And as you can see, Alice is very different from the image, the John Tenniel pictures that you know from the Alice books. Meanwhile, Robert Fawcett, the mathematical lecturer, had gone to fight in the Crimean War, and the new dean appointed Dodgson in his place. So here are his self-portrait of what I look like when lecturing, and also one of his student mark sheets. But at first his teaching load was very heavy, and his teaching didn't always go well. As he wrote in his diaries, "I have 5 pupils whose lectures need preparing for. Blackmore in for a first at Easter, doing end of differential calculus. Rattle in for a first in mods this time, needs special problems, etc., and very probably high differential calculus, a little integral calculus, and spherical trigonometry." And with all these different topics, he found it very difficult to keep up to speed with all of them. In fact, later he confessed that, "I am weary of lecturing and discouraged. I examine 6 or 8 men today who are going in for little go, and hardly one is really fit to go in. It is thankless uphill work, goading unwilling men to learning they have no taste for." But fortunately and gradually things improved, and he continued as the college lecturer in mathematics for the next 25 years. Incidentally, it was around this time that Dodgson started his popular writing. His pen name of Lewis Carroll, which he used when writing for children, derived from his real name. Lewis is a form of Ludwig, his middle name and his mother's maiden name, while Carroll, or Carolus, is the Latin for Charles. But not all his whimsical writing was for children, as we'll see. Dodgson had a great enthusiasm for geometry, a subject he spent much of his time teaching to students for the Oxford examinations. And even here, he sometimes let himself go. For example, let's recall the famous Pythagorean theorem on right-angled triangles, that the area of the square on the hypotenuse, the longest side, is equal to the sum of the squares of the areas of the squares on the other 2 sides. Here, a squared plus b squared equals c squared, although such an algebraic equation would have meant nothing to the Greeks. The Greek result was all about the areas of the geometrical areas of squares. So what did Dodgson write about it? This was in the middle of an otherwise serious treatise on Euclid's parallel postulate. About the Pythagorean theorem, he said, "It is as dazzlingly beautiful now as it was in the day when Pythagoras first discovered it and celebrated the event, it is said, by sacrificing a hecatomb of oxen." That's 100 oxen. A method of doing honour to science that has always seemed to be slightly exaggerated and uncalled for. One can imagine oneself, even in these degenerate days, marking the epoch of some brilliant scientific discovery by inviting a convivial friend or 2 to join one in a beefsteak and a bottle of wine. But a hecatomb of oxen, it would produce a quite inconvenient supply of beef. But the Greek geometer that Dodgson was most involved with was not Pythagoras, but Euclid, who probably lived around 250 BC. Euclid's most famous work, The Elements, is claimed to be the most printed book after the Bible. It consists of 13 books, actually rolls of papyrus originally, on geometry and arithmetic, and is logically organized, starting with some basic axioms, and then some simple deductions, then further ones, until a massive hierarchy of results has been produced. Regarded as excellent training for the mind, it was used for teaching for some 2,000 years, particularly in Victorian times, with over 200 editions of the Elements appearing in England alone in the 19th century. Some exceedingly successful. There's one by Todd Hunter, for example, that sold 500,000 copies. On the right at the top is Robert Potts's edition, which is Dodgson's preferred version. And below is a drawing that Dodgson produced showing the hierarchical structure of the results in Book 1 of the Elements. Here, everything leads down to proposition 47, which is a proof of the Pythagorean theorem. Now, Dodgson was a great enthusiast for the Elements, knowing it intimately and having to teach from it for all the Oxford examinations. But a movement was growing to replace Euclid in schools by newly devised geometry texts that included more practical topics such as surveying. Dodgson was bitterly opposed to these aims and wrote his best-known geometry book, Euclid and His Modern Rivals, which appeared in 1879. Dedicated to the memory of Euclid, it's a detailed attempt to compare Euclid's Elements favourably in every case with geometry texts by a dozen authors of the time. And it's written as a drama in 4 acts with 4 characters. There's Minos and Rhadamanthus, who are 2 of the judges at the entrance to Hades, here recast as Oxford examiners with a whole pile of exam scripts to mark. Herr Niemand, who's a German professor, and Euclid himself. And between them, they consider each rival book in turn and manage to demolish it, leaving Euclid as the only option. It's a very wittily written book, but it has lots of very, very serious geometry in it as well, showing that Dodgson really knew his Euclid inside out. In fact, Dodgson wrote a great deal on geometry, as you can see here. Some were editions of the books of Euclid, and others were scholarly texts, but many were pamphlets written for students to help them to understand the Elements for their Oxford examinations. And of particular importance in 19th century geometry was the issue of Euclid's so-called parallel postulate. And I'd like to mention this briefly. One of the unproved assumptions that Euclid made is shown on the left at the top. It is that if you have 2 lines, and if another line crosses these lines in such a way that the angles A and B add up to less than 180 degrees, then the 2 original lines must eventually meet, as shown in the diagram. So that was an assumed result by Dodgson. But a lot of people felt that it was more like a theorem, something you ought to be able to prove from the other axioms. And so they tried to prove it, and this happened for 2,000 years, and no one was successful. Alternatively, they tried to prove equivalent results, and the equivalent result is the one in the middle, that if L is a line and if P is a point not on the line, then there's exactly one line through P which is parallel to L. And when I say these 2 results are equivalent, that means that if we assume either of them, then we can prove the other from it. But do we have to assume either? For the previous 2,000 years, as I said, mathematicians believed that you didn't, and had tried to prove them from the 4 much simpler axioms that Euclid had stated. And as Minos claimed in Euclid and His Modern Rivals, an absolute proof of it from first principles would be received, I can assure you, with absolute rapture, being a delusive hope that mathematicians have been chasing from your age down to our own. Euclid replied, I know it, but I cannot help you. Some mysterious flaw lies at the root of the subject. But as it turned out, neither result can be proved from Euclid's 4 other axioms, because there are strange geometries, now known as non-Euclidean geometries, that satisfy the other 4 axioms, but where these results are all false. Now, Dodgson's contribution to the subject was a pamphlet called A New Theory of Parallels, which exhibited an even more obvious result that's equivalent to the first 2, and which he felt pedagogically was a better one to choose. Namely, that if you draw a hexagon inside a circle, then any one of the 6 segments lying outside the hexagon has a smaller area than the whole area inside the hexagon. Seems pretty obvious. And he took that as an axiom. But again, to prove it, you need one of the other results. It's equivalent to the other results. Later, he replaced the hexagon by a square, but in the non-Euclidean geometries, those results don't hold either. Meanwhile, Charles Dodgson was getting to know the Liddell family, taking Alice and her sisters on educational tours of Oxford. He also took them on boating trips, such as the famous excursion in July 1862, when he invented the famous story of Alice's Adventures Underground, as he originally called it. And here's his original manuscript with his own drawings. Well, Alice's Adventures in Wonderland, as it was eventually called, was published in 1865 and proved to be a magnificent success. And in later years, the story went around, which Dodgson firmly denied, that Queen Victoria had been utterly charmed by it. "Send me the next book Mr. Carroll produces," she demanded. The next book being an elementary treatise on determinants, with their application to simultaneous linear equations and algebraical geometry. She was not amused. We don't know whether the story is true, but he actually did deny it in print, but not until about 30 years later. So what are these determinants, and what have they to do with simultaneous linear equations with geometry? Let me try and explain quickly with an example. If you look at these two equations here, we can solve them the way we did at school. And the solution turns out to be x equals 2 and y equals 1. So let's check that. The first equation has 4 2's and 7 1's do indeed give 15, and 3 2's and 10 1's do indeed give 16. Alternatively, we can find the solution by drawing the two lines that correspond to these equations. And if you draw those, you'll see that they cross at the point x equals 2, y equals 1. But we can also solve these using determinants, and this was a well-known method at the time. Well, I say well-known, but in fact determinants, although they went back to 17th century Japan, it was only in the 19th century that they became popular. And there's a textbook on determinants by someone called Spottiswoode around 1851, and as we'll see, Dodgson then wrote his own textbook. So what is a determinant? Well, briefly, a determinant is a number here associated with a 2 by 2 array of numbers. Here you can see A, B, C, D. If the numbers are A, B, C, and D, their determinant is a number A times D minus B times C. For example, the determinant of this array here, 4, 7, 3, 10, is 4 times 10 minus 7 times 3. That's 40 minus 21, giving 19. To solve the equations, we next do the same, but with the 4 and 3 in the first column replaced by the right-hand sides of the equations, 15 and 16. And then we do the same with the second column replaced by 15 and 16. And if you work out those two determinants of these two arrays here, they turn out to be 38 and 19. And finally, you take 38 and 19 and divide by the 19 you had earlier, and you get the correct answer, x equals 2, y equals 1. Now, that's not necessarily the quickest way of doing it, but it does work for... But if you're used to it, it becomes very routine, and it works for any similar pair of equations, and can also be generalized to more equations and to larger arrays of numbers. And here are some of the examples that Dodgson gave. On the left is a 4 by 4 determinant. That's where you've got 4 equations and 4 unknowns, so it involves 16 numbers. While on the right is an even larger example. You can see lots of equations at the top. But calculating these larger determinants can be really quite awkward and time-consuming. And what Dodgson did was to introduce what he called his condensation method, where the calculations of these larger determinants can be reduced to calculating only lots of 2x2 ones, which of course we know how to do. So given any example, however big, Dodgson's method was to reduce it to dealing with just these 2x2 ones and using the AD minus BC formula. Well, he wrote these as a book, but although his book on determinants wasn't a great success, his condensation method did cause some interest and was presented by Bat Price on his behalf at a meeting of the Royal Society. And in fact, his Royal Society paper shown here was the only research paper that he ever published. Now, for a while, Dodgson's condensation results were forgotten, but recently they've resurfaced, and they've turned out to be very useful in a number of current areas of mathematical research, in matrix theory and in combinatorial mathematics. Well, let's turn out to the next topic, which is mathematical logic. Because throughout his life, Dodgson was interested in the subject, and there are many logical allusions in the Alice books. Believing that symbolic logic could be understood by his many child friends, he devised the game of logic, published under his pen name of Lewis Carroll to make it more popular. And the purpose of it was to sort out logical syllogisms. So what are syllogisms? Well, dating back to Aristotle, they're pairs of statements called premises that lead to a conclusion. For example, if you know that all men are mortal and Socrates is a man, you can easily deduce that Socrates is mortal. Well, Carroll's syllogisms were much more entertaining. For example, if we know that no bald creature needs a hairbrush and that no lizards have hair, we can deduce that no lizard needs a hairbrush. And Dodgson was very, very good at making up dozens and dozens of more jolly examples of that type. But Carroll's method for finding these conclusions, which he taught to children and adults alike, used a board with red and grey counters that were placed on sections of the board to represent two true and false statements of the form some x or y and no x or y. I won't go into the details, you'll find them in both of these books, but he gave instructions for how to use them, and on the right is another example which opens his book on symbolic logic. So the example he has there is, supposing you know that story of yours about your once meeting the sea serpent always sets me off yawning. And you know that I never yawn unless when I'm listening to something totally devoid of interest. Then by using the counters in the way that he shows, and which one can explain, you can deduce that story of yours about your once meeting the sea serpent is totally devoid of interest. And as he remarked, if, dear reader, you will carefully observe these rules and so give my book a really fair trial, I promise you most confidently that you will find symbolic logic to be one of the most, if not the most, fascinating of mental recreations. And as I said, he taught most of its contents to many children, some of them as young as 12 years old, and he found them to take an intelligent interest in the subject. And Carroll also devised rules and notation for sorting out his syllogisms without having to use a board and counters. Here are 10 of his entertaining examples, together with their logical formulations. So if you know that all pigs are fat and nothing that is fed on barley water is fat, well, you can go through the motions there and work out the conclusions. So here are 10 of the 60 examples that he had in his symbolic logic for people to work on. And you can either solve them by using the board and counters or by learning the notation that he used there. But there's no reason why we should limit ourselves to just two premises. His later logical puzzles, known as soriteses, a horrible word, involve more than two. And for example, this sorites has 5 premises. Because suppose we know that no kitten that loves fish is unteachable. No kitten without a tail will play with a gorilla. Kittens with whiskers always love fish. no teachable kitten has green eyes, and that no kittens have tails unless they have whiskers. You can then conclude immediately, or by using his counters, that no kitten with green eyes will play with a gorilla. So that's useful to know. But we don't need to stick to just 5 premises, and the most ingenious of these examples went up to an amazing 40 or 50 premises. He comes up with examples, a huge long list of premises, and if you work through them all systematically, getting rid of one of these at a time, then you can deduce the conclusion. Quite amazing the way he managed to think these things up. Well, before we leave this subject, let me show you some of the diagrams that Carroll used to present connections between sets of objects. Many of us are familiar with the 3-circle Venn diagram, introduced by John Venn of Cambridge in 1881, and showing the connections among 3 sets. As shown on the left, Venn also extended the idea to 4 sets, except that circles can no longer be used, and then to 5 sets, but unfortunately one of the sets was in 2 bits, with that ellipse in the middle, and he couldn't take it any further. Meanwhile, Dodgson came up with some diagrams around the same time, and these were much better. Starting with the board that he used for syllogisms, that you can see at the top in the middle, he then extended his diagrams to connections among 4 and 5 sets, which you can see here, and then to 7 and 8, as you can see on the right. And in principle, his drawings can be extended to connections between any number of sets. And I always find it's rather a pity that Venn gets all the publicity, whereas Dodgson's diagrams, being much flexible, are not better known. To change topic again, in 1867, Christchurch elected a governing body for the first time. An act had to go through Parliament for this, instead of being run by the canons of Christchurch as previously. And Dodgson now found himself voting on various issues, such as appointments to academic posts and the choice of a college architect. And he soon developed an interest in the study of voting patterns and constructed several examples to show the failure of conventional methods. So he took a lot of the well-known examples, first past the post, he took, and simple transferable vote, and he came up with some very clever examples to show what was wrong with each of them. And here's his example of the unfairness of the simple majority or first past the post system. So you've got to think of this, read down the columns. So you suppose there are 11 voters and 4 candidates A, B, C, and D, and that each voter has arranged the candidates in order of preference. So here, reading vertically, the first voter ranks them in the order A, C, D, B, and so do the next 2. The next 4 have ranked them in the order B, A, C, D, and so on. So which candidate overall is the best? For Dodgson, it was candidate A, who's considered best by 3 of the voters and second best by all the remaining 8. But in spite of this, the usual winner is candidate B with just 4 votes, even though B is ranked worst by over half of the voters. Well, Dodgson was one of the most important people writing about voting. There had been some work done in the 1790s by Condorcet in France, but Dodgson's contribution was very important. So he wrote several pamphlets, such as this one, which was actually supplied to me and for the book by Edward Wakeling, editor of Dodgson's Diaries in 10 volumes and author of the chapter in the book on recreational mathematics. Now, Dodgson also wrote about parliamentary representation. In those days, a constituency like Oxford University, Oxford and Cambridge universities were themselves constituencies, right up to the Second World War. Quintin Hogg was, in fact, the Member of Parliament for Oxford University just before the Second World War. And in the 1860s, when he wrote about these things, 1860s and 1870s, Oxford University had 2 members of Parliament. And he wrote a rather witty pamphlet, which I won't go into today, but I have given in some of my other lectures, where he was trying to get rid of Gladstone, who was one of the sitting candidates, who was far too liberal for Dodgson, and bring in one of the others. And he gave a pseudo-geometrical diagram to illustrate that. The point is that Dodgson very strongly believed in fairness for all. He certainly wouldn't have approved of a voting method in which a vote of 52 to 48, say, to choose random numbers, would leave almost half of the electorate unrepresented. He had a strong belief in fairness, and as a result, he was a strong supporter of proportional representation, and he wrote this pamphlet in which he worked through the mathematics involved. I think his favourite system would have been, say, a constituency where there are 5 members, and that means that quite a lot of different shades of opinion could have been represented by that. Well, in the end, some of Dodgson's recommendations were adopted in England, such as the rule that allows no results to be announced until all the voting booths are closed. Pretty obvious, but it didn't happen then. Whereas other ideas, such as his methods of proportional representation, were not taken up. But as the philosopher Sir Michael Dummett, who died a few years back, and himself an expert on voting, later remarked, "It is a matter of the deepest regret that Dodgson never completed the book that he planned to write on the subject. Such were the lucidity of his exposition and mastery of the topic that it seems possible that, had he ever published it, the political history of Britain would have been significantly different." And I thought back in 2011, when we were considering the alternative vote, and an awful lot of rubbish was written in some of the newspapers, what they would have learned if they'd gone back to Dodgson and read some of his writings on the subject. Dodgson was also concerned about the fairness of tennis tournaments at a time when seeding didn't exist. There's a Wimbledon of the day, and Dodgson was quite concerned that a player who'd been beaten was mortified to see the second prize awarded to a player quite inferior to himself. And as Dodgson wrote, "At a lawn tennis tournament, where I chanced to be a spectator, the present method of assigning prizes was brought to my attention by the lamentations of one of the players who had been beaten early in the contest and who had the mortification of seeing the second prize carried off by a player whom he knew to be quite inferior to himself." So here on the right is an example that he gave with 32 players ranked in order, with number 1 being the best and number 32 the worst. Now in the first round, 1 will beat 2, 3 will beat 4, 5 will beat 6, and so on. So it's the odd-numbered players that survive to the second round. Now in the second round, you've got the second round. The survivors are the players 1, 5, 9, and 13. So 1 beats 3, 5 beats 7, and so on. They go on to the third round. And then 1, 9, 17, and 25. And then the last round is just 1 and 17. And finally, player 1 wins, as he should. But the second prize is awarded to player 17, who had started in the lower half of the ranking. Now, Dodgson thought that was very unfair, and after much thought, Dodgson devised a scheme whereby the top 3 prizes are awarded to the best 3 of the players. We turn now to Dodgson's interest in recreational mathematics. In the 1850s, he had tried his hand at some teaching in a local school, St Aldate School, opposite Christchurch, where he varied his mathematical lectures with stories and puzzles. Here are a couple of them, and I'll leave it to you to work out how they work. But suppose we start, well, it says start with the number 1. Take it in turns to add a new number, any number up to 10. And the person that reaches 100 is the winner. So how can I ensure that I always win? So, for example, suppose I choose 1. And then if you choose 5, say, giving 6, then I'll say 12. If you then add 7, giving 19, I'll say 23. And it turns out that whatever you say, I'll reach 100 first and win, so it's a good game. And you might like to try and work out how that works. And here's the other one. Choose any number, reverse it, and subtract the smaller number from the larger. Select any digit other than 0, remove it, and tell me the sum of the remaining digits. I will then tell you which number you removed. And again, it's not particularly difficult to work out how that works, but I'll let you think about that as an exercise for the reader. Dodgson always believed that recreational topics were a useful vehicle for conveying more serious ideas, and throughout his life he enjoyed showing puzzles to adults and to his young child friends. And here's a geometrical favourite of his. You start with an 8 by 8 grid of 64 squares, and you cut it into 4 pieces. You then rearrange these pieces, as shown on the right, to give you a 5 by 13 grid, which has 65 squares. Where did the extra square come from? It's a very clever puzzle, this. I think it's one of his favourites and one of mine too. The answer, which I'll give you, lies in careful drawing, because if you draw the right-hand diagram very carefully, you'll find that there's a very, very thin diamond-shaped hole in the middle, a parallelogram whose area is exactly equal to 1 square. So they don't quite fit together. There's this little gap in the middle. Well, I was looking through his diary for 1890, and I saw that Dodgson generalized this problem, showing that it works for all the numbers given here on the right. So you've got your square, and if you choose A and X and draw these 4 pieces, you can then match them together like that, and a similar paradox shows up. What Dodgson didn't mention, although he must surely have realized it, was that the method works because all of the numbers on the right turn out to be Fibonacci numbers, and Fibonacci numbers have that property that the square of 8, for example, is 1 less than the one on either side, 5 times 13, and so on. So the same thing happens for all of those. There's always that one little parallelogram in the middle. Another famous problem of his, hotly debated in various Oxford common rooms, was his monkey and weight puzzle. Briefly, you've got a rope going over a pulley. On one side is a monkey, and on the other side is an equal weight. The monkey starts to climb the rope. What happens to the weight? And there's a lot of discussion, as I said, in the various common rooms. Some of his colleagues thought that the weight went up. Others said it went down. Some people said it went up or down uniformly, and some said it accelerated. Anyway, everyone seemed to disagree. In fact, it moves up in such a way that the monkey and the weight always remain at the same level. But it's interesting that there's quite a lot of discussion then, and in the book you will actually see a letter between Dodgson and Bat Price about that very, very problem. In the 1890s, Dodgson became interested in number-guessing puzzles. You probably did these when you were a child. Think of a number, add 5, multiply by 3, and so on, and then I can tell you what the number you thought of was. Well, Dodgson's were much more sophisticated. So you've got a person thinking of a number, and after a series of questions and arithmetical calculations, the original number can be deduced. So here's a particularly ingenious one in his handwriting that he invented. The only intermediate answer that the inquirer needs to ask is whether the result is odd or even, and how many times the final result is divisible by 7. So let's just go through this. You can do it if you want. Think of a number. So suppose B thinks of 23. Multiply by 3. Is the result odd or even? Well, B gets 69 and says, it's odd. A said, add 5 or 9, whichever you like. B chooses to add 9 and obtains 78. A says, divide by 2 and add 1. B obtains 40. A, multiply by 3. Is the result odd or even? B obtains 120 and says, it's even. A, subtract 2 or 6, whichever you like. B subtracts 6 and obtains 114. A, divide by 2 and add 29, or 38, or 47, whichever you like. B chooses to add 38 and obtains 95. A then says, add 19 to the original number and tack on any figure you like. In other words, add it to the end of the number. B tacks on 5, so he's got 42, and then he gets 425. Add the previous result, obtains 520. Divide by 7, neglecting the remainder, gets 74. Again, divide by 7. How often does it go? 10 times. The number you thought of was 23. Quite a remarkable exercise, that. And the first time he did it, he actually, the method didn't quite work out rightly, but eventually he got it all sorted out. And you can see the answer if you buy the book. Or you can think it for yourself. Dodgson's last piece of mathematics is recorded in his diary for the 19th of December, 1897. Sat up last night until 4 a.m. over a tempting problem sent to me from New York. To find 3 equal, that means equal in area, rational-sided right-angled triangles. So you can think of right-angled triangles, say, with a whole number of sides that all have the same area. I found 2 whose sides are 20, 21, 29, and 12, 35, 37, but could not find 3. Well, as it happened, Dodgson was closer than he knew, because if you double the sides of his 2 triangles, you get 2 of the 3 triangles in the smallest available triple. So the smallest answer is actually twice that, which is 40, 42, 58, and then twice the next one. So you've got 24, 70, 74, and 15, 112, 113, all with area 840. And that's the smallest answer. And in fact, there are infinitely many solutions to that problem. There's another one, which I've just given here, where the common area is 10,920. Well, at the end of 1897, Dodgson went to Guildford to spend Christmas with his sisters at the house they lived in called Chestnuts, which is still there. If you're in Guildford, go and see it. He was intending to finish volume 2 of his Symbolic Logic, but while there at Christmas time, he caught pneumonia. He died just before the book's completion, and his manuscript version didn't turn up until the 1970s. If it had appeared at the time, he might have been regarded as one of the greatest British logicians of his time, say the greatest between Boole and Russell. And certainly Bertrand Russell was impressed with a couple of Dodgson's logical paradoxes. In fact, I was talking to a logician, an Oxford professor of logic, and he said that the 2 logical paradoxes that that logicians most talk about are 1, Russell's paradox, and 2, a paradox of Dodgson called Achilles and the tortoise, and not the same as the Zeno one in ancient Greece, but there's a very, very clever logical paradox, which I think no one has really sorted out now, even to this day. Anyway, Dodgson died there in Guildford, and here's his posthumous portrait in Christchurch Hall, together with 2 of the stained glass windows now in Daresbury Church, where he had been baptized. And if you go to Daresbury Church, there's quite a nice little Dodgson exhibition in the church. It's up in Cheshire, fairly near Warrington, I think. Coincidentally, Dean Liddell, whose daughter Alice had been so much a part of Dodgson's life, died just 4 days later. And here's part of their joint eulogy in Christ Church Cathedral. As the preacher said, within the last few days, Christ Church has lost much. And though the work that bore the fame of Lewis Carroll far and wide stands in distant contrast with the Dean's, still it has no rival in its own wonderful and happy sphere. And in a world where many of us laugh too seldom, and many of us laugh amiss, we all owe much to one whose brilliant and incalculable humour found us fresh springs of clear and wholesome and unfailing laughter. And that's the best tribute to Dodgson that I know. Thank you very much for listening.